Hi, this is Rocket. Today we're going to look at the source code of Elmo from LNLP. I'll put this code link onto my video description. Now let's get started. To better read and present this code, I download it and open it using PyChar, like this. I suggest you can do the same thing while reading source code. This code is written in PyTorch. First, we can take a brief look at the general structure of the code. What we can do is click the minus sign here to compress the code. And you can see there are three classes here. First one is Elmo. And the second one is character encoding. And the last one is Elmo bidirectional language model. If you recall the architecture of Elmo, it has a character encoding layer, bidirectional LSTM layer, and Elmo layer. And by looking at the name of the class, we can have a good guess here. Probably the Elmo character encoding just implements the character encoding layer of Elmo. The Elmo ILM just implements the bidirectional LSTM layer. And the class Elmo just implements the Elmo layer. So with this high-level assumption of the code, we can go deep and take a closer look. So first, at the top of this file, we have a bunch of import and also setting the login. And also in PyTorch, the standard way to write a model is to inherit the torch.nn.module class. And we have an init function which describes how we should instantiate this class. And down below, we would have a forward function which defines the forward propagation of the model. With these rules in mind, we can start at the beginning and read the code. Now we can take a closer look about the meanings of input arguments. So the best way is just to, click these comments. It has all the information here. I would briefly mention some of the parameters here. The rest are self-explanatory. For the options file, it contains all the hyperparameters for this model. For the weight file, is that if for some layers, such as character encoding layer, if you don't want to train it from scratch, you can just load it from the weight file. And for the parameter number of output representations, it controls how many representations we can use to represent a token. If we set to 3, then it means we can use character encoding layer, first bidirectional LSTM layer, and second bidirectional LSTM layer to represent a token. You can see we can also specify if we want to do layer norm, we want to do dropouts, if we want to cache, things like that. And this scalar mix parameters with type list of float specifies the weight when we compute Elmo embedding. In the comments, it gives an example. So if we specify in this way, that means we only care about the first layer of the bidirectional LSTM when we compute Elmo embedding. And this module parameter, if specified, that means we don't need to train our bidirectional LSTM. We can use it as it is. Otherwise, we would train the bidirectional LSTM from scratch. That's all for the input arguments. Now we can compress the comments and see the init function. As you can see, all the input arguments mentioned above are listed here. And going down to line 113, if the bidirectional LSTM module is not null, we would just use as it is. Otherwise, we go to the else case, where we would create this module using this function, Elmo by LM ourselves. For the rest of few lines, we just populate the input arguments into our local variable. And next, we would loop all the number of representations. And for each representation, we would compute a weight and save it in the list. That's all about the init function, where we just save all the input arguments for a local variable so we can use it in the forward function, where we compute the forward propagation of the model. Let's first look at the input and output of this forward function. We have two input arguments. First one is the input sequence with shape, batch size, number of words, and the maximum number of characters to represent a word. The second one, word inputs, is a cached vocabulary. In the later step, we can look up character embedding from it. And notice that the word inputs, which means the cached vocabulary, is optional. So we don't have to provide the cached information. We can just compute everything from scratch. In terms of the output, it's a dictionary with two keys. So the first key is the Elmo embedding with shape, batch size, number of words, and embedding dimension, which means for every word, it would have an Elmo embedding. And the mask has shape, batch size, number of words, so it would mask out some of the words. Now we can further look at the code. So first, we do some sanity check on the shape. We first get the shape of the input, and if it is in a list format, we just reshape it to the same shape as here, batch size, number of words, and number of characters per word. Otherwise, we just take as it is. For the second input arguments, word inputs, we do similar things on the shape. If it is in the list format, we would convert it to the tensor format by this view, and the new shape will become batch size, number of words. Otherwise, we just take this inputs as it is. Next, we would call this Elmo LSTM function. In this function, we have both character encoding layer and the bidirectional LSTM layer. Since it's better to look at the general structure of the code before diving into too much details, we can just check the output of this function, and then we can move further down below. In order to trace this function, we can just control-click it. And now you can see we define this Elmo LSTM in our init function. But you can see we have another function, Elmo capital BILM. So we need to trace further down. And now you can see this is another class, Elmo bidirectional language model. And this is its init function. In order to check the output, we need to look at the forward function. And you can see the output is another dictionary with the first key being activations with this shape, and the second key being mask with batch size, number of words +2. Also notice the activation is a list of tensor, and each tensor would have this shape, which means that every element in this list represents one layer of the output. Recall that in our previous introduction, we would have multiple layers to represent a token. So we would have character encoding layer, bidirectional LSTM layer. So all the output are aggregated in this activation, represented as a list of tensor. With this information in mind, we can go back. And this is our output. And in the next two lines, we just get the value. So layer activation, we just get the value of the activation key. And this mask, we just get the value of this mask key. And next, we just compute the Elmo embedding, which is the weighted sum of all the layers output represented in this layer activations. To understand how we do the weighted average, we need to start another trace. As you can see, since we start the for loop here, and we call the length of this self scalar mixes, we need to start trace here. And now you can see this is what we defined in our init function. And you can see every element is a scalar mix, and it calls another class, capital scalar mix. We just further trace down. So now we find another class, scalar mix. And you can see from the comments, it would compute a scalar mix of n tensors. This is a weighted sum. And if we go down to the forward function, we would say the same thing. So it computes a weighted average of the tensors. And you can see the output is also a tensor. So the input is a list of tensor. And when we compute the weighted average, the output is a single tensor. We can briefly go over how this weighted average is computed. If you go down, there's a variable called normed weights. And this is a softmax with values from the scalar parameters. If we further trace down, this self-scalar parameters is from the initial scalar parameter. This one is a list. If it is none, then by default, it's 0, 0 times the mixture size. And this mixture size is number of layers to represent the token, as we get from the activations before. And this syntax just means we will create a list with mixture size amount of element, and each element has value 0. But definitely, we don't have to use the default value. We can set it. If we didn't set it right, there will be a configuration error, as shown here. And now we can go back. Let's assume we use the default value. So every element is 0. And when we do the softmax, that means the weight of every layer representation is the same. That's the normed weight. And let's assume we don't do layer normalization. So as you can see, we just loop through the weights and its corresponding tensors. And we just use weight times tensor. And we sum everything. And times the gamma as a hyperparameter. So this thing is a weighted sum of every tensor. If we do the layer normalization, we just use weight times layer normalization of the tensor. And in the end, we still sum all the stuff and times gamma. So with this understanding, we can go back. To here. From our previous code walkthrough, each scalar mix would give us one kind of Elmo embedding because it will provide some weights. And if we have length of the scalar mixes, we would have a list of these different Elmo representations. And we just append each of them into this representations list. I think the motivation here is that for different tasks, the weight when we compute the weighted average is different. So we can give different weights and compute different Elmo embeddings that's specific to each task. And we can store all the information in this representations list. And next, we just reshape the output if necessary. But you can see in the else case, we don't have to do any reshape. And finally, we just return this value, Elmo representations and the mask. And if we go up to check the comment again, as you can see, the returns is a dictionary with key Elmo representations and a mask. So for Elmo representation, it's a list of tensor, which means we have a list of Elmo representations based on different tasks. And the mask has shape, batch size, number of words. That's all about the Elmo layer. We can do a quick recap. So first, we would reshape some of the input if necessary. Basically the input here and the word input. which is a cache, and this is optional. And we would send those two inputs into the Elmo LSTM layer. The output of this Elmo LSTM would have representations from different layers. And also, it has a mask. And to compute Elmo representations, we have a bunch of weights represented as scalar mixes. And for each set of weight, we would compute an Elmo representation. And we would store it in this representations list. And finally, we just return these Elmo representations and mask in a dictionary format. With this big picture of how we compute the Elmo embedding, we can dive deep into this Elmo LSTM.